organized. I want to talk about something that's very simple. It seems to be a good strategy. It's joint work with a former student of mine called Paul Colognese, who is currently supported by a grant from a foundation that pays him to fight artificial intelligence. So I assume it's a bit like a Terminator. It all sounds very, very exciting. And this is some work he did with me when he was my PhD student. And the other thing I do in these things is try to bribe the audience. So in keeping with this, I have some topic, which I will ask on a very confident person to open negatively around. Okay, so I want to talk about entropy and a result for translation surfaces. So first of all, it doesn't sound very promising because you might think that the translation surface has zero entropy, making it less an interesting problem. And secondly, I want to talk about some sort of rigidity result of some kind, in a very modest form. For those of you that are interested in such things, the notes from my lecture, which means I have scanned the lecture notes, they are on my webpage. And you can get there by simply Googling my name. From somewhere near the top is a link which just downloads a PDF file that he does. If you Google Pollicott, then the first thing that comes up usually is Great Pollicott, which is made that refers to a town in England. And if you go to my webpage, more interesting perhaps is a picture of me from 1982, where I haven't changed the tool. So let me give some motivation. Motivation. And the motivation comes from the hyperbolic setup. So in that case, I'm going to get on with the surfaces. So I'll let M be a topological surface. And so it has interesting structure. I'll assume that it's got negative Euler characteristic. And so here's a picture of such a surface. So possibility is compact. And then the game is that once you fix the surface, you can put different metrics on it. So I'll let G be some sort of space of C infinity Riemannian metric. But since I'm only interested in the dynamics, I'll assume that they're negatively curved. The curvature I'll denote by kappa subscript G. G is just going to be one of these metrics, and it's going to map me into negative numbers. I'm interested in metrics on here, which have the property that they are fixed off of surface, changing the metric. And I'm also going to assume that the area is fixed. So for each of these metrics, I'll look at the area associated with that Riemannian metric, and I'll assume it's equal to a constant. And if my calculation is correct, the constant should be 2 pi times the Euler characteristic. But whatever it is, it's just a fixed area. So now we have a fixed topological surface, but we can change the metric. So we may get a long thin surface, or maybe a lumpy surface. That's the same genus, of course. And what we want to do is to say something about it. Oh, and I should also say that an example of metrics inside here would be metrics of constant curvature -1. So P contains metrics at constant curvature -1, assuming what the area calculated is correct. Another flip. And that would be by Gauss-Bonnet.
in common with lots of people in England, I learned differential geometry from the 5 volumes of Michael Spivak. And on one of them, he has a picture of an elephant carrying a banner that says, "All the way we go on it." Very positive thinking. So to have something dynamical, we introduce the entropy. And in this case, it's just going to be a function, so we can associate the entropy. So that's the function A, which is going to take it from the space of matrix into the positive reals. And the way it's defined for our purposes is going to be as follows. It's given by, for a given metric, you associate the number and its limit, t tends to infinity of 1 over t, is the growth rate of the logarithm. And sometimes forget the log, so I can do it as well. What's the logarithm of? It's the logarithm of the number of closed geodesics, which with this particular metric have length less than 2. And this corresponds to the geodesic flow topological entropy by an old result of Sinai from 1956. So for every metric on my surface, same topological surface, metric changes, then we can look at the topological entropy. And maybe there are some comments, so let me just make some remarks. So one is that indeed, this is the topological entropy of the geodesic flow for a given surface and that particular metric. And the second comment is that this, of course, was improved a bit later as a result that says that if you want to count the number of closed geodesics whose length is less than t, then that is a stronger result, which says that's asymptotic to e to the h times t over e of h times t. And this was by Modulus from 1969. This was announced in a 2-page paper, pretty short on details, but that was the way it was going to be. And let me make the extremely pedantic comment that by here, a geodesic is just a locally distance minimizing curve. Which we knew already, but I want to refer back to this. Okay, so it's a very simple setup. We have a surface, we wobble the metric in some particular way, and there's a numerical invariant, which is the topological entropy. And then there's a famous result due to Hamiltonian cut-off. So say, I want it from circa 1982, I think. And what it says is that the numerical value of the entropy, range of different metrics, is minimized at metrics G of constant curvature. Of constant negative curvature. Providing I got the numbers right, the curvature is just identically equal to -1 for the ones that minimize the entropy. This is a very kind of well-known result. And by way of some pointless picture, we could think of the space of a metric, which of course is infinite dimensional, but in my picture it becomes 2-dimensional. And then above that, we're plotting the entropy, so it's a kind of graph, and there'll be a bit where it's minimized, so it might look like how it's going to look. Might look a bit like that. This is not going to be entropy as some function, and it will be h g, and so this will represent metrics with constant curvature. So it's a very old but very nice result. And so the aim is we want to try to generalize this in some weak sense. So aim, or find an analog, to find an analog for translation surfaces. So this poses some immediate problems. What do I mean by this? What is the translation surface? Would be helpful to know. And then what do we mean by the entropy? What's this numerical thing going to be for these translation surfaces? And then how are we going to say anything about minimizing it? And stuff like that. So that's the idea. So if you didn't like, if you're not a geometer, which I'm not, and you don't like negatively curved surfaces, don't worry, they just disappear. And now let's talk about translation surfaces. So here we go. Translation. I'll say very little about translation surfaces in detail, due to the fact that I know very little about translation surfaces in detail. We'll do our best. So what I want to do is I want to consider some sort of polygon sitting inside the plane. So X is going to be a polygon in R2 with parallel sides. Parallel sides, which we identify. So rather than draw something very complicated, let me just concentrate on one example. So I have to draw a polygon that sits inside the plane with the sides which are being parallel. The hardest thing here is trying to get the sides to look parallel. So here it's meant to be some sort of letter L shape. It's meant to be a polygon sitting inside the plane. And so if I look at these sides, so for example, this side is going to be identified with this one, which is parallel, and perhaps this one will be identified with this one, and then we can identify this guy with this guy, and then the fourth side, this bit, is identified with that guy. So these are meant to be like Roman units. Okay, so if we were if I'd been naive enough just to draw a square and identify the sides, I'll just get a standard flat torus. Here I haven't, I've drawn something more sophisticated, inspired by the fact that I keep flying to Luton Airport. And if you fly to Luton Airport, it's called London Luton Airport, and they write it on outside as L, and then they have the A looking like something bent over like that. But anyway, so this is still a polygon sitting inside the plane, and I would call it X0, and henceforth I'll particularly be talking about this rather than the general case. And when we do these identifications, if I erase my reference to London Luton Airport, if I identify these sides, then we get something that's a little bit like a surface. In fact, it turns out to be something which is genus 2. And the corners of each of the squares you see here, they're going to be orange apparently. So these guys all get identified to the same points, which I will just denote here. So what we get is a surface which is flat, it's got zero curvature everywhere, but it goes a bit crazy at this surface point. Crazy being a technical. So basically, this is going to be a genus 2 surface, which has got zero curvature, except at the singularity. What happens at the singularity is that we have our surface. Let me draw another copy of it. And you want to know what happens in the neighborhood of this point to understand what it looks like. So here are a bunch of points. So these are the guys that get identified when we fold up our polygon We cut it out of the plane, identify the sides, and then get the picture over here. But let's imagine instead we went on an excursion around one of these singular points identified. And we could perhaps do that in a different color chalk, possibly one that's going to be invisible to the view. Oh, wow. So let's imagine that we start somewhere. We start at the bottom, and an ant or some such small critter walks around here from this side to this side, and then he reappears over here, and he continues his voyage, which will be the second step. Then he reappears up here, and then he goes around here, his third leg. Over here, he comes around here, just using the identifications. And then where does he go? He starts, then he comes up here, that's identified with that, goes around here, so that's his fifth trip. And then this point's identified with this one, so the sixth one down here is going to be that guy. So he gets to here. This point is identified with this guy. So the seventh part of his journey is with the step 9. 7 is to here. And then the 8th part is this point is identified with this point. So we come up here, we get to that point, and he's finished just back where he started. So some small critter like an ant walking around this singularity will take a long time to get there. And in fact, the total angle, if you add up all of these angles, is going to be 6 prime. So with an angle 6 prime. So basically, that's what the surface will look like. So what we'd like to do now is to say the following. Well, can we, given this particular surface, associate a number like we did for a negatively curved surface up there? So we'd like to associate some value, which we'll call the entropy. Not really an entropy, but it's a number anyway. And the question is, how are we going to define it? Well, let's take a look at the definition we had up here, due to Sinai, and then let's just copy that. So in order to do that, we have to know a bit about the closed geodesics on this surface. And so, let me, in anticipation of this, write closed geodesics on, well, in general, a flat surface, a translation surface, but I'm usually thinking of X0 or something like that, and an entity. Some number which is going to characterize the surface. And the first observation is that when one looks at geodesics, well, they are, as they were before, they're distance minimizing curves. So locally distance minimizing. And if you are on a flat space, then of course you're going to get a straight line. The shortest distance between 2 points is a straight line. I don't know the scores on that. And what happens is that you have 2 possibilities. First of all, you may get families of parallel lines. Or alternatively, you get something more complicated, which are concatenations of straight lines between the singularities, which are generally called saddle connections. So the first case is pretty much like in the case of a standard flat torus, just for arc coefficient T2. So in my picture, you could imagine that there's going to be a curve that looks like the following. It's going to go from the top to the bottom, and these points are identified, and that's going to be the closed geodesic on my surface. But then all the guys that I get by translating this are also going to be closed geodesics. They all minimize distance locally, and they all have the same length. And this case, we're going to ignore. And the other possibility is that we have a geodesic which encounters some of these singularities. And if you encounter a singularity, the effect of this is you get very confused and go all over the place. So for example, we might start at this point here, I'm copying my picture, and then go up to the top. But this point here is identified with this point, so we might then reappear somewhere near the bottom. Somewhere. I did it the wrong way around. I should have started here, I think. Yeah, I could have started here. So that will be later. So this will be my first step. I started a singularity down here, and I returned to a singularity, which is actually the same point on the identification. That will be my first part of my closed geodesic. And the point at the top, well, he's actually identified with all these other points, but in fact, he'll re-emerge at this point and then go up to the top and then reappear at the bottom because these sides are identified and then go up to there. So that would be 2 and 3. And that can give me a closed geodesic. So I'm creating a closed geodesic which is made up of bits of straight lines connecting up copies of the singularity. Which ones are allowed? Well, the ones that actually are still different to minimizing when you go through the point. But the point is there's lots of them. And with this, what we can now define the entropy to be the growth rate. Yeah. Hello. Yes, probably, yeah. Let's conceal that part for the moment. There are an awful lot of these closed geodesics knocking around. So the point is that when I said that the cone angle was 6 pi, what happens is that when you go into one of these singularities, well, you can't use 2 pi because that kind of bends too much. But the other 4 pi allow you to shoot out in random directions. So you get lots and lots of closed geodesics. You go into it. It's like when you go into a restaurant and you have a revolving door. You're not quite sure if you're going in or coming out again. You get kind of confused in the middle. But these guys, these geodesics, they go into the singularities and they can come out in different places with different angles, lots of different angles. And so using that, the point is that they grow exponentially fast. So here's the definition. And this definition is kind of based on one of gentlemen called Dankworth from 2014. I believe he's a student of Hammesha. And what it says is that if you give me a translation surface, x, then I'll define an entropy to be a growth rate of a number of closed geodesics, skipping the ones that are just parallel ones. So it will be the limit, which will be this, t tends to infinity, 1 over t of the log of the number of, indeed, closed geodesics of length less than or equal to 2. And here for closed geodesics, let me call the either or cases something. Let me call this guy A. Let me call this B. So we're firmly in the B case. Okay, so I guess there's a number. So we've got some exponential growth, and it's coming from the nature of these singularities. Is that a question? Yes, Euclidean, right. So the singularities spin you around, but the distance you go is simply the length on the polygon. But it is the Euclidean right. Back. Thank you very much. Well, the case A has the disadvantage that there are uncountably many closed geodesics because of the translation. But if you considered equivalence classes, then there would be they grow they grow at the polynomial rate, so they wouldn't contribute to this particular value. So you could either say, well, if we have infinitely many, let's identify them all, but then they won't contribute to this. My strategy is let's ignore that. I thought it was a winning strategy, but it's the one I'm following. Okay, so and in the same way that Margulis had an improvement on the Sinai formula for the entropy, there is actually an asymptotic formula associated with this. And so this would say what we think it would say. If we look at the number of closed geodesics from X of length less than or equal to T, then you might guess that it's going to be asymptotic to e to the H times T over H times T. And that is indeed the case. This is T tends to infinity. And this is a result of Eskin and Raffi. I'm unable to give a date due to the fact that I don't have the money. So this is an asymptotic which corresponds to this case. It's just these straight lines between the singularities at the top. So the class of closed geodesics which keep bouncing around like pinball balls, between the singularities.
So, the Margulis result from 69 is for
Negative
Riemannian manifold
Riemannian manifold, real thing,
with negative.
with negative curvature.
And then this is where
Correct. Yeah, so it's a different set. There tend to be a lot of those guys, negatively curved guys, and maybe not so many flat guys. But in negative curvature, we have the advantage of what the body to play with. You know, transfer measures for foliation, stuff like that. Here we don't have that luxury, so we have to do something else. But still, it's possible to do it. Okay, so what do I want to do? So now I've introduced the setting. The setting is I want to take a surface or a family of surfaces. I want to associate the number, and then I want to do something. What do I want to do? I want to do something which is reminiscent of the statement I made of the result of matter. I'd like to understand how this entity varies as I change my surface in some appropriate way. How am I going to do that? Well, let me think out where I'm going to write it for a start. I want to look at a family of translational surfaces. Okay, so I've defined how to associate to a given translational surface the entropy, it's the growth rate of the closed curves. And the question is, well, what can we do if we have a family of these guys? Okay, so we can construct new surfaces. From our original guy called X0. So X0 was not only an example, but he was also going to be a fundamental thing. Having erased him is really helpful. Let me write X0 up here to remind you. And in this picture of X0, the idea was that all of these lengths were actually equal to 1. Something I neglected to mention before. They're all like unit cube things. There's 3 cubes stuck together, just like the London Newton inside. Okay, so what I want to do is now construct some new surfaces just from this guy. So if I'm given this particular picture, I've just obscured, how am I going to construct new guys? Well, what I want to do is to apply SL to R. I want to move it around. So what I want to do is I want to mess around with this guy X0 and take the orbit under the linear action of SL2R, because it's a thing to do. So the new surfaces are going to be of the form, I write it here maybe, it's going to be SL2R, It's an orbit of this applied to x0. What does that mean? It just means that for each of my polygons sitting in the plane, I apply a matrix from this guy by the linear action. So A is S L C R. And if there's any doubt what I mean by that, I'm not going to make that simple sort of idea. So here's back to my example. And so I had my surface, which was looking different each time I draw it, but it's meant to look the same. It's meant to be three boxes, suitably arranged artistically. This is meant to be x0. And then what I do is I apply matrices from SL to R. So for example, I could apply the matrix 1, some number 0, 1. And this should be a shear. So it should take me to something that's the same height, but leaning over to the right. Use your imagination. That's what I artistic skills and high this. Which is not to be a sheared version of that. And so I call this guy, well, down here I call it the matrix like that. So this one is called 1 over W 0 1 times my original surface x0. And here W is just going to be some real. Okay, I can do that. Or alternatively, I could apply some other matrix. And another fun one, of course, is to look at lambda 0, 0, 1 over lambda. So it has to turn with 1. And then the image of this would be, well, if lambda is bigger than 1, it will be long and thin. We'll get flattened from that, like that. So that's meant to be my image. It would be lambda 0, 0, 1 over times x0. So I can do this with any of the matrices. Yes, it preserves the area. And here lambda, I guess, should be a positive number. If you agree with the picture, then probably it would be bigger than 1. Or if it was smaller than 1, maybe it becomes 4 instead. But we don't really care. Okay. And so the question I want to ask is the following. Well, if I look at this bunch of surfaces, which one is going to minimize the entropy as I have to find it up there? So the question is, for which surfaces in this orbit, so for which A in SL2R is H of A of x0 minimized. So in the case of negative curvature, the cutoff result, we looked at surfaces which have negative curvature, but more importantly, the same area. And then we wobbled around the metric and we found the entropy smallest precisely when we had constant curvature. Here we're moving around our surface, albeit in a somewhat limited way by translating, by applying these matrices, but it gives us a three-dimensional family. And the question is, well, for these guys, when is the entropy going to be, this entropy going to be minimized? So we're not in a situation where negative curvature makes any sort of sense. So there must be some other results. And so our result is the following. So this is a theorem which is, I guess, by Colognese itself. And what it says is that when we look at our nice function applied to all the surfaces we could get by shearing and plating and concentrating does nothing, flattening, stuff like that. So this when we look at this function, zero there, when we associate to this the entropy, then this is minimized. When something is true, and it's when the image AX0 is triangulated . by equilateral triangles. Which have singularity to each vertex. Try to give an example of what happens. Version of this example. Maybe the negative curvature coming up as a into the past where it belongs. I can now talk about this case. So my claim is that for any surface in the orbit of x0, that would be a particularly nice surface, the entropy is going to be minimized for a certain class of these guys. And so here is an example of where you get to these things. Here's an example. Let's assume that we went back to x0, our starting point, which doesn't look the same every time I draw it, but it's meant to be. It's meant to be just 3 unit boxes. This is x0. And so what we want to do is we want to apply some matrix to get something else. And the claim is at the end, we want to get something that looks like a bunch of equilateral triangles, which will stretch my drawing skills beyond uniform hyperplicity, in this case beyond anything that looks reasonable. So it's going to be a picture in the right way. Okay, so you have to imagine that all of these triangles are equilateral triangles. And how did I get there? Well, what I did, let me just move that down a bit so it looks more reasonable. How did I get there? I got there by applying a matrix, and I call the matrix A with a triangle. That's going to be my final surface. I'll get there by applying some matrix. And what matrix is this? Well, I'm going to first of all, if we get from the right again. So from this side, I'm going to be applying 1.5, 0, 1. So this is a shear where I shear by a half. And then I'm going to scale by a value of lambda. So this would be like this, where lambda is, last time I calculated it, it's going to be the square root of 2 over the 4th root of 3. And so if you take this thing, which you can imagine as being boxes, and you try to shear it into the shape to make them equilateral, then a lightning calculation, which is sometimes correct, would be you use the matrix, which is probably hello. X0 is indeed a very specific example, but it's representative of another class of very, very specific examples. So it works for any squared tile surface for which the vertices are all singular. Doesn't work that way. Partly because, of course, if you take a more general surface, there's no reason that you're going to get in the orbit for anything that's with the tile in the Hi. No, if I was doing it properly, I'm not sure I'm capable of doing it. You can, of course, if you take different matrices, then you can cut and paste the image to get an isometric surface. So there are going to be lots of matrices that give rise to the same surface with the same geometry. But I'm just giving one example. Hey, that's not good. I can help. That's it. You can ask the using an action. Anyway, you're saying it's okay. So if you want any polygon in the plane, it will be infinite because we can just keep translating by things that look like this. But if we're only interested in the isometric surfaces, it's going to be 2 in the plane. So it's finite, and if you do it properly, it will be modularized by using words that but if you're interested in just pictures, you allow this thing to get tilt over as far as you like, then there will be many more. Stuff like that. I feel guilty, but I'm probably wrong. Okay, great. Hello. Yeah. Yes, that's right. So there are lots of examples of square tiles, all of which have a common name, some of which are German, and I can't remember. Well, this one I can actually draw, and it'd be here. But you can't do it very generally, but you can do it for a bunch of examples. Okay. Right. So that's the statement of the theorem, and it says in my notes, there are two non-isometric examples, of which I give them one. In response, maybe to these questions. Hello. The other one comes by, I think, tilting in the opposite way. I'm not sure you get exactly the same thing. But let me be a bit vague. It's in the paper, but my co-author is more the translation skill be better. I just provide the draft. I don't remember what that. Being super. Okay, so having carefully timed this law, yeah, in this case. So in this case, it's an if and only if thing. So if you actually plot the thing, then it's going to have exactly two numbers, which will be one of which will be this, no, this, and then one complementary. Yeah, what's it? If it's in this orbit, we're in good shape. You give me another surface which is not in the orbit of X0 and it was. Yeah. I mean, X0 is here not just as an example, it's something that helps it. There is a slightly broader class, as I was saying to the famous probably, but it's still a bit limited. There's still square tiles. But there are people that make a living out of square tiles. So let me try and say something about the proof. So in the notes which are online, there is in fact more details, but I'm not sure I can do all these things in the intervening time. Maybe if I give all the chocolate to Francois, I want to get the extension from home. Next slide. So here is going to be a proof. Did I number any section? I did. But let me call this 4, and I will prove that it's not going to be very complete, but maybe it will give you some idea. So the proof is based on looking at lattices. So we can characterize, we need to characterize the entropy in the way we can use it, characterize this entropy using some functions. Very cryptic comment. And these functions are based on lattices. These are not lattices like general lattices which are in the from Lee group or something. These are just lattices in the plane, of which my favorite, of course, would be Z2. It would be even better for children, right? But that's okay. So here is a picture of a lattice, Z2. So we have a bunch of points. And tends to be evenly spaced, but somehow that didn't quite work in the drawing. But then I actually don't want to have 0 for some reason. So let me get rid of 0, which in my picture is here. It'll be 0, then 0, 0. And a typical guy, of course, would just be N, M. N. So actually, I'm going to look at Z2 minus 0, 0. What would you do? Except, of course, these guys don't look like the difference of 0, 0. What if I use a different color? And then, so where are these matrices going to come in? Well, the matrices, of course, are going to come in because we apply them to the lattice. So we have our matrix A, it's still an element of SLR. But instead of applying it to some polygon, we can apply it to these guys. And so then we'll get another sort of lattice thing. It will look even worse, because I'm even worse at doing these things. You have to use your imagination at the stage. like that. And so 0, 0 wouldn't have gone anywhere. That guy's still 0, 0. But all the other guys have moved around a bit. And so in particular, there'll be points over here like this guy, which I'll call V. And then the game is that what I've drawn a picture of is A applied to Z2 minus 0, 0. That's the image of this lattice under minus the points under the matrix A. And then I look at all the points I can get. And if I have a point inside here, I'm interested in its distance from the origin. Just a point in R2, not a distance, you do figure this one. And we've given my notes. V equals this one. Zero. Keeping an eye on the clock. What do we want to do? Well, somehow we want to get the entropy in this. I mentioned it before, it hasn't appeared yet. What's he got to do with these guys? Well, it's the following. I can introduce a function that will tell me what the entropy is in terms of the measurement. And so, given a value t greater than 0, and a matrix I want to try out, which is going to be SL2R, I can define a function. And the function I will define to be f of t and a, since I just bothered to introduce them. And it's given by an infinite series. And I sum over the vectors in this image. So that would be v in a of z2 minus the point. And what do I sum? I sum e to the minus t, so the t makes an appearance, times the norm of v. I can do that. It's a function. An interesting function. I think that depends on your viewpoint, but let me say something about it. For our purposes, the good news is it's going to give us a way to get a handle on the entropy. The way that works is very warming to the heart of people who used to do. So let me just make the following observations. The way I've defined it, it actually makes sense. So in fact, this function converges to say f of t of a as a function of t converges and is analytic for the real part of, well, no real part, t greater than 0, in good shape for all positive values. And secondly, it's going to be monotone for people. All of these kind of objects. Let me draw a 30-pointless picture. So here is meant to be t. I'm going to plot the function ft against the sky. So in particular, we have the following. So here's meant to be my graph. The function is meant to be f t of a as a function of t for a fixed value of a. And then the claim is that lemma 1 is that the entropy of my associated surface satisfies, what does it satisfy? It satisfies that it's the value of t, which this takes a specific value, and the specific value is 1/2. So you take the value of 1/2, and you read off the value down here, and that's going to be the entropy of your surface. So now we characterize the entropy as a value where something happens. So if you like Poincare series, it's a bit like that, or zeta function, but it's a bit like that. This is the characterization of each thing. So let me just rush through the remaining 6 lines, which constitute for the proofs. And so to compare things, just not to break this into the board. So to compare functions, we need something else. And there is a lemma, lemma 2. And this says that, let's assume that we have our favorite surface, the one we like. So let's assume something. You're going to assume? We'll assume that A delta is the particular matrix which gave us the triangulated surface. So assume A da 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 is an element of S, L, R. Giving the triangulated surface, U related surface. And let's assume we've got some other guy which we want to compare him with, which doesn't do that. So let's assume that A is another guy. So S, L, C, R, which is not giving triangulated surface. Then we can compare the associated functions, and what we get is that the F, E for the good guy, this matrix is actually going to be strictly smaller than F, C of A for all T greater than 0. So we can compare these two functions. And then the proof follows immediately from the picture. So all we have to do is stare at these two lemmas long enough. This picture will take me about 30 seconds to draw. So the theorem follows from the two lemmas. Theorem. What is that? Well, because if I draw the plot again, I have one guy and I have another guy. So the one associated with the time with this surface is going to be less than the other guy. So this would be F for the good guy. I'll make any more difference here. A delta for the triangulated guy. And the other curve is going to be above that. It's going to be up here. It's going to be F, C, A. And of course, we can read off the entropy by fixing the value of half and looking at the picture. So in this case, we get H of a delta of X has to be smaller than the value of the entropy for any other surface that we have. And that's just from these two values. Thank you very much.
Thank you. Any question?
Right. So on the orbit, entropy is going to be smooth as you like. If we were wild and predictable and thought to the surface another way, it's at least continuous, probably Lipschitz, and maybe more, but I don't know. There is not directly anything. So I mentioned the result of Eskin and Rapid about counting things. That's what we developed. And in that case, there is some transport for well, they actually use transport. You don't need to use transport. You can use infinite numbers. But yeah, I mean that's not used directly in this group. I don't know. I don't know. I only understand it in very limited cases, so I can't really answer the question. What's clear is that the reason that the entropy gets big is because you may get singularities getting close. It's like, well, I think it's like anything. If you get singularities very close, then you get things bouncing backwards and forwards. So that gives you wisdom. So you've always got to go off to infinity somewhere, but I don't know about minimizing it.
How much?
Very little, in fact. The proofs are extremely amusing, but unfortunately, you don't get them. I only do the boring bit. The amusing bit you don't get. So the first one, the first lemma is kind of easy-ish. The reason being that the entropy, like any decent entropy, is going to be the outsider of some series, as we've learned. And this series can be written in terms of an expression like this. Basically. Yes, you would. So the half actually comes from the cone angle. It's because it's, as one would have guessed, it's 6 minus 2 divided by 4, obviously, or something like that. I don't know why. Something like that. Yeah, it's based on the cone angle. It would be more or less the same sort of formula. Let me just say that we got stuck for a while because we didn't know how to do this last part. And this is interesting, I play, because if you replace the v by v squared, like here, the norm of v by v squared, then it actually becomes a theta function in another way. And that's been studied and people know how to minimize it. And so we just use some classical analysis, such as Bernstein's theorem, to convert a result of Montgomery into this particular case. So we scrape up other people's results.
No other question? Thank you again. Next talk is at 5:10.